Hello everyone, this is Dr. A classes for BTech students. This lesson introduces the Engineering Geology course. It is designed to provide BTech civil engineering students with essential geological knowledge. The learning objectives of the course is understanding the fundamental principles of geology and their application to civil engineering projects, developing the ability to interpret geological maps, data and reports, gaining practical knowledge of site investigation techniques and their significance. What is geology? Geology is the branch of science that studies the earth, its composition, structure, and the processes that have shaped it over time. The term geology has been derived from the Greek word geo and logos. Geo means earth and logos meaning study. It is the study of earth, its origin, structure, composition, and the nature of the processes which have given rise to its present position. Geology encompasses a wide range of topics, including the formation of rocks and minerals, the movement of tectonic plates, the evolution of life, and the history of Earth's climate. It plays a crucial role in understanding natural hazards like earthquakes, volcanoes, and landslides. Geology also has practical application in fields like mining, engineering, and environmental management. How geology evolved. Geology as science evolved over centuries through observations, theories, and technological advancements. Key stages in evolution of geology are ancient observations, early theories, early scientific approaches, and modern advancements. Ancient observations. Ancient civilizations like the Egyptians, Babylonians, and Greeks were not just observing rocks, they were actively using them. They, they needed strong durable materials for constructing pyramids, temples, and other monumental structures. This required knowledge of different types of rocks, their strength, and how to work with them. They crafted tools and weapons from various rocks such as flint for arrowhead and obsidian for knives. This involved understanding the properties of different stones and how to shape them effectively. They relied on rocks for building dams, aqueducts, and irrigation systems. This necessitated knowledge of rock types and their suitability for different engineering applications. While practical applications were crucial, the Greek philosophers took a step further. They began to think more deeply about the natural world, pondering questions about how earthquake occurred and what fossils represented. The significance of these early observations are, while they were not having been called geologists, these early civilization and thinkers were making crucial observations and asking fundamental questions about the earth. The insight, however rudimentary, provided the foundation for future generations of scientists to build upon. The Greek began to move beyond simply using rocks to understand them, marking a crucial shift towards a more scientific approach to study the earth. Early theories. The development of geological idea was not confined to a single region or culture. Different civilizations and religious traditions contributed to the evolving understanding of the earth. Some early explanations for the formation of different rock layers were tied to biblical account of great flood. These explanations often intertwined religious beliefs with observations of the natural world. Al-Biruni, a Persian polymath, was a prominent figure in the 11th century. His work covered a wide range of subjects, including geography, astronomy, and mineralogy. Islamic scholars during this period made important observations and advancements in the field related to geology, such as mineralogy, geography, and the study of natural phenomena. Early scientific approaches. Aristotle proposed that the rocks were formed under the influence of heat and pressure. This idea, while not entirely accurate in its specific details, reflects early attempts to understand the formation of rocks. Strabo, a Greek geographer, emphasized the gradual changes that shape the Earth's surface. This observation was significant because it pointed towards the long-term nature of geological processes, a concept that would later be formalized in the principle of uniformitarianism. Observation of erosion and sedimentation emphasizes the importance of direct observation in understanding geological processes. The observation of how water and wind erode rock and transport sediments is fundamental to understanding how landscapes are shaped over time. Avicenna, a Persian polymath, made significant contribution to geology, including his observation on sedimentation and mountain formation. His ideas helped to advance the understanding of how sediments accumulate and how mountains can be uplifted. Leonardo da Vinci, this renowned figure, recognized the role of water in sedimentation. His observation on the movement of water and its ability to transport and deposit sediments were crucial for understanding the formation of sedimentary rocks. These observations, though made centuries ago, laid the foundation for the development of modern geology. They demonstrate the importance of careful observation, critical thinking, and the gradual accumulation of knowledge in advancing our understanding of Earth. Modern advancements. Industrial revolution, with its booming mining and construction industries, created a strong demand for a better understanding of Earth's resources and geological features. This increased demand led to increased funding of geological research, establishing geological surveys in many countries and fostering the growth of professional geology. James Hutton introduced the principle of uniformitarianism, stating that the present is key to the past. This groundbreaking concept suggested that the geological processes we observe today, such as erosion, sedimentation, and volcanic activities, have been operating throughout the Earth's history. Werner proposed the theory of Neptunism, which suggests that all rocks were formed from the crystallization of minerals in a universal ocean that gradually receded. Neptunism was influential for a time, but it was eventually challenged by observation that contradicted its predictions. The debate over Neptunism spurred further research and led to the development of more accurate theories of rock formation. Charles Lyell's principle of geology expanded upon Hutton's ideas and provided strong evidence for uniformi- uniformitarianism. Lyell's work was highly influential in geology and other fields. His ideas on gradual change and the immense age of the Earth significantly influenced Darwin's theory of evolution. The development of geological time scale was a major achievement in geology. It was made possible through the careful study of fossils and the stratigraphic records, the layering of rocks. And the geological time scale provides a framework for understanding the major events in Earth's history, from the formation of planets to the evolution of life. Alfred Wegener proposed the theory of continental drift, suggesting that the countries were once joined together as a single landmass, that was called Pangaea, and hence and have since drifted apart. These developments represent significant milestone in the history of geology, demonstrating the gradual accumulation of knowledge, the importance of observations, and the experimentation and the ongoing refinement of our understanding of Earth. How engineering geology evolved. Engineering geology has evolved from a relatively nascent field to a critical discipline for modern civil engineering. Its evolution has been driven by the increasing complexity of the engineering projects, the development of new technologies, and growing awareness of the importance of environmental sustainability. Many early engineering projects faced setbacks and failures due to the unforeseen geological issues such as unstable ground or unexpected water seepages, etc. These failures underscored the need for a more systematic and scientific approach to understanding the geological factors that influenced engineering projects. This led to a growing recognition of geology as a crucial discipline for civil engineering. William Smith, a pioneer work in geological mapping, provided a crucial foundation for engineering geology. His map and stratigraphic studies helped to identify and understand the distribution of different rock types and geological formation across the landscape. The development of key concepts like stratigraphy, the study of rock layers, and the rock mechanics, the study of the mechanical behavior of rocks. These concepts provided a framework for understanding the stability and behavior of geological materials under stress. By the 20th century, engineering geology had emerged as a distinct discipline within civil engineering. The development of soil and rock mechanics, pioneered by figures like Carl Terzaghi, provided the tools and techniques to analyze and predict the behavior of geological materials in engineering contexts. This knowledge was crucial for designing stable foundation, tunnels, and other structures. Engineering geology played a crucial role in planning and construction of large-scale infrastructure projects such as dams, bridges, and tunnels. Modern engineering geology utilizes a wide range of advanced tools and techniques, including GIS, that is Geographic Information System, for mapping and analyzing geological data, remote sensing for obtaining aerial and satellite imagery to study geological features, geological surveys, geophysical surveys for investigating subsurface conditions using techniques like seismic surveys and ground penetrating radar, computer modeling and simulation. Sophisticated computer models and simulations are used to analyze complex geological problems and predict the behavior of structures under different conditions. There are growing emphasis on environmental geology and sustainability, considering the environmental impact of engineering projects and developing sustainable solutions. What are the different subdivisions of geology? Geology has several major subdivisions, each focusing on different aspects of the earth. The subdivisions are physical geology, geomorphology, mineralogy, petrology, crystallography, stratigraphy, paleontology, structural geology, hydrology, groundwater, geophysics, geochemistry, photogeology, economic geology, mining geology, and the engineering geology. Physical geology deals with the geological processes which brings about changes in the crust and upon the surface of Earth. Geomorphology deals with the description and interpretation of landforms. Mineralogy is the study of the characters of minerals. Petrology is the study of rocks in all their aspects, including their mineralogies, textures, structures, origin, and their relationship to other rocks. Crystallography is the study of characters of crystals. Stratigraphy deals with the study of the stratified rocks, especially their sequence in time and the character of the rocks. Paleontology, it deals with the study of ancient life, determination of environment, and evolution of organism. Structural geology is the study of three-dimensional distribution of rock units, that is, the study of rock structures such as folds, faults, etc., that have resulted from the movement and deformation of the Earth's crust. Hydrology and groundwater is the study of the geological factors relating to Earth's water. Geophysics combines physics and geology to study Earth's interior and dynamics. It explores structure, physical conditions, and evolutionary history of the Earth as a whole. Geochemistry is the study of chemical composition of minerals and rocks of the Earth. Photogeology deals with the interpretation of the geological and geomorphological features as well as the various lithophases on the aerial photograph. Economic geology is the study of economically valuable geological materials. Mining geology deals with the method of mining of rocks and minerals deposited on the surface and the subsurface. What is engineering geology? Engineering geology is the application of geological knowledge in engineering works that ensures safety, efficacy, and economy of engineering project. It involves evaluating rocks, soil, and groundwater conditions, providing information about geological hazards that could impact a construction project such as earthquakes, landslides, subsidence, flooding, etc. Considering geological factors from the initial planning stage, engineering geology helps to ensure that construction projects are safe, efficient, and cost effective. Importance of engineering geology. Engineering geology plays a vital role in ensuring the success of construction projects by providing crucial information about the geological conditions at a site, identifying potential hazards, and optimizing the design and construction processes. Engineering geology helps to assess sites suitable for construction, identifies potential geological hazards, optimize design and ensure stability of structures, prevent project delays and cost overruns. Key concepts in engineering geology. Soil mechanics, that studies behavior of soil under load. Structural geology, that gives information about folds and fractures. Hydrogeology, that studies groundwater flow and its effect on construction. These areas are crucial for engineering geologists to understand and apply in their work. By careful considering by carefully considering the properties of rock, soils, and groundwater, and by understanding the geological structure and processes at a site, engineering geologists can help ensure the safety and stability of engineering projects. Role of an engineering geologist. Engineering geologists evaluate the geological condition at a proposed construction site to determine if it is suitable for the intended project. They help in understanding the composition, strength, and behavior of rocks and soils that are crucial for designing foundations, tunnels, and other structures that would be stable and long lasting. Engineering geologists use geological information to design structures that can withstand hazards and to develop mitigation measures. They evaluate groundwater condition to prevent issues like flooding, seepage, and erosion. Engineering geologists identify potential geological hazards that could impact a construction project. By identifying and addressing potential geological issues early on, engineering geologists help prevent project delays and cost overruns. Engineering geologists identifying the geological condition help optimize the design of structures to ensure their stability and safety. Application of engineering geology. Engineering geology plays a crucial role in designing and constructing a stable foundation for building and structures. Geotechnical engineers assess the soil and rock conditions at site to determine the appropriate foundation types. This includes evaluating the soil's bearing capacity, its susceptibility to settlement or liquefaction, and the potential for groundwater issues. By considering these factors, engineers can design foundations that will support the structures safely and prevent future problems like settlement or collapse. Tunnel construction presents unique challenges due to the confined space and the potential for encountering unexpected geological conditions. Engineering geologists assess The rock types identifying potential hazards like faults, fractures, and groundwater inflows, and recommend appropriate construction methods. They also play a crucial role in monitoring the stability of the tunnel during excavation and construction. The stability of dams and reservoir is critically important to prevent catastrophic failure. Engineering geologists evaluate the geological condition at the dam site, including the foundation material, the surrounding rock slopes, and the potential for seepages. They also assess the potential for earthquakes and other geological hazards that could impact the dam stability. Road construction requires careful consideration of geological factors, especially in the mountainous or hilly areas. Engineering geologists assess slope stability to identify potential landslide hazards and recommend mitigation measures like retaining walls or drainage systems. They also evaluate the suitability of road construction materials such as aggregate and fill materials, ensuring that they are durable and resistant to the weathering. At the end of the presentation, these are some of the self-assessment questions. Go through each questions carefully. Answer these questions based on your understanding of the topic. Review any concepts you are unsure about. The questions are: discuss how geology as a subject gained importance. Explain the branches of geology in detail. Define engineering geology, how it evolved. Write an account on the significance of geology in civil engineering, how the geological factors play a major role in construction failure. Discuss. Thank you for joining this lesson on engineering geology today. Hope you found this presentation informative. At the end, don't forget to like and subscribe the channel Dr. A Classes for more engaging lessons on core subjects of civil engineering. Thank you.